Now we'll go ahead and try some examples writing equilibrium laws for things that include solids and pure liquids. If we look at this example, we have calcium oxide solid plus sulfur dioxide gas is in equilibrium with calcium sulfite solid. So we look at this and we know K sub C is the concentration of the products over the reactants. Since my only product is a solid, that doesn't get included, so I just write 1 over. Solid here doesn't get included, and so the only thing that goes in my equilibrium expression is the concentration of that sulfur dioxide gas. So I get K sub C is 1 over the concentration of sulfur dioxide gas. Now go ahead and pause the video while you fill in these two for the mercury chloride and the ammonium chloride. Okay, looking at this, did you get the same thing I did? We have solid mercury chloride, liquid mercury, and chlorine gas. So the only thing that goes into our expression is the chlorine gas. So K sub C is 1 over Cl2 gas. Now if we look down here, we have two gases as reactants and a solid as a product. So the K sub C is 1 over the ammonia concentration times the HCl concentration. Now, the next thing to explore in basic information about equilibria is how we can manipulate these equilibrium equations. We've already said that equilibria can go back and forth in both directions at the same rate. So we can manipulate things just like we did in Chem 111 with Hess's law. Remember in Hess's law we said if we have something that can be done in steps, we can add up the information from each step and we'll get the same energy. It's kind of the same thing that we're going to do here as we manipulate these equilibria. So let's just start looking at two generic equations. Equation 1 says A is in equilibrium with B, and equation 2 says C is in equilibrium with D. So let's start with equation 1. We're going to take this and I'm going to turn it around. So B is in equilibrium with A. Now, if we look at this, we can write the equilibrium constant, and I'm going to call this K for 1 reverse, 1R, because I'm reversing it, and that'll be the concentration of A divided by B. Now, if we go back to our equation 1, and we write the K sub C for this, it's equal to the concentration of B divided by A. So if we look at these two equations, let's look at K sub C related to K sub 1R. Do you notice that they are reciprocals? So what that tells us is that if I turn an equation around, my new constant, K1 reverse, is equal to 1 over K sub C 1. I'll call this for equation 1. So anytime we turn an equation around, we just take the reciprocal of the constant. Now let's look at what happens if I try and add some things together. Let's look at equation 2. We can write K sub C2 is equal to the concentration of D divided by the concentration of C. So now let's look at what happens if we add these two equilibria. We have A is in equilibrium with B and C is in equilibrium with D. So adding together all the reactants and all the products, I get A plus C is in equilibrium with B plus D. So my K value for my added equations is equal to the concentration of B times the concentration of D divided by the concentration of A times the concentration of C. Now if I look at my two original K values, KC1 and KC2, we can see that my new added equilibrium constant, K add, is just these two multiplied together. So KC1 times KC2. So if we are adding equations, then we go ahead and we multiply the two K values. So anytime we add things, we multiply. If we go in reverse, we take the reciprocal. Now let's look at the next thing when we multiply by a coefficient. We did this in Chem 111 in Hess's law. So instead of my original A is in equilibrium with B, where my KC1 was equal to B concentration over the concentration of A, now I'm going to multiply this whole thing by a coefficient. So 2A is in equilibrium with 2B. So my K multiplied, I'll call it, is equal to the concentration of B squared, because of the 2 and the coefficient in the balanced equation, divided by the concentration of A squared. So when I look at the relationship to this first equation, that's equal to KC1, the whole quantity, squared. So if we multiply an equation by a coefficient, we raise the K value to that power. So let's go ahead and look at some mathematical examples. Here is the equilibrium constant for this equation. 2SO2 gas plus O2 gas is in equilibrium with SO3 gas. If I know K sub C for this equation, what is the value of K sub C for this one? Well, if we look at this, we've taken the original, we've turned it around, and we've divided by 2 or multiplied by 1/2, because I have 2 moles and 1 mole yields 2 moles. Flipping this around, I get 1 mole is 1 mole and 1/2 a mole. So it is reversed and it's divided by 2. So my new K, because it's reversed, will be 1 over my original K. And because it's divided by 2, it'll be raised to the 1/2 power, or the square root. So now that's equal to the square root of 1 over 7.0 times 10 to the 25th. And that's equal to 1.2 times 10 to the negative 13th. Now go ahead and try this next one, and I'll review that on the next video. This is the end of this video.